Hi, physics. Here we are on chapter 18, section 2, and we're doing the second part, starting on page 641. And we're comparing resistors in series and parallel. We've already talked a little bit about series. That is where one comes right after the other. And I didn't draw them as resistors here, just trying to show the concept of series. One follows the other, just like people walking down a path. Parallel is where they're all next to each other. And that'd be like walking three of you down the sidewalk and you're all next to each other instead of front and back of each other. Well, what happens to a circuit if we have all of our resistors, in this case light bulbs, all in a row? And the electrons have to go through this light bulb and then through this light bulb and so on. What happens if we were to take out a light bulb or the light bulb were to fail and the resistor burn out? What happened to our circuit? Well, if the electrons can't go through this light bulb, it can't go through any of the rest either. And the whole thing fails. The most famous example that we have that you'll see is oftentimes Christmas lights are strung up this way. And you lose one, and suddenly you lose a whole section of the circuit. They've gotten a little bit better in trying to make multiple circuits and so forth so you don't lose all of the light bulbs when one goes out. But there's another way we could wire things. What if we could wire them in parallel? Now, conceptually, a lot of people struggle with drawing, so I'm going to draw several different things just to illustrate it. First of all, series. You've got a resistor, and I'm not the greatest artist when it comes to drawing resistors, but they're all in a row. R1, R2, R3, and they come back around to the battery, and around they go. Again, right angles, even though the metal is curved. Parallel, well, we can draw it sort of like this. We can draw it so that the wires split and go two different directions and then come back together. They go on to the battery, and we have a circuit. This being R1 and this being R2. Now, there's several things we need to talk about in this circuit. Again, first of all, they're next to each other. So let's say that we took one of them out. Could we still have, if these were two light bulbs, would the light bulb still work? The answer is yes. This one will work just fine. In fact, it might even get a little brighter because the electrons all have to go this way. They can't go two different directions. So we can draw this many different ways. I'm going to draw it a little bit differently, and it's going to be the exact same circuit. It's just going to look a little different. You see, instead of drawing a forked thing, I'm going to draw it like this, and this is R1, and this is R2. And there's more right ways to do it. Let's come back to this guy. The electrons here, they have just as much push to go this way as they do this way. And so the voltage drop from across parallel resistors is always the same. So in our book, we have this drawing here. Even though there's a little more wire to get to here, it's the same voltage here as it is here to get across these resistors. So you kind of have to look at a circuit and mentally say, okay, well, the voltage from here to here is the same as the voltage from here to here. And it'll impact the equation the same whether you're here or here compared to here and here. So if this is a 9-volt battery, the voltage drop across here is 9 volts, and the voltage drop across here is 9 volts. Now, just because they're parallel does not mean that the current is equivalent. In this circuit, current is equivalent in all three because the electrons have the same way to go. Here, the electrons can go two different ways, so the current may not be the same. The only way the current is the same through both resistors is if the resistors are the same size. Then the resistance is the same on both ways, and the amount of electrons going through both is the same, which add up and will be double here or here. Now, what about calculations? When it was series, all we had to do is just add this one plus this one plus this one. That was easy. Well, not quite so easy. Oh, by the way, there is the definition of parallel. Not quite so easy when it comes to parallel, a little more complicated. Here's a diagram again trying to show parallel circuit, and that is the same as drawing it this way or this way. If there's a bulb that has less resistance, more electrons will go through that bulb. So let's say that the bulb with this one is very resistant, this one is less, this one will have more electrons going through it and use more electricity. All right, so let's look at the math a little bit. The current going through any one of these circuits, let's say that this is I1 and this is I2, together they must equal the I total. The current going through this has to split this way, and over here it'll be the same, I total. These two together, so we're going to have I total equals I1 plus I2, and if there's more resistors in parallel, we would just keep on adding. Well, that's designated here in our book. We also know that V equals IR, and we can rearrange this so that I equals V divided by R. So what if we took this and substituted in for all of these guys? All right, so we could say V over R total will equal V1 over R1 plus V2 over R2, and so on. Well, in parallel, the V1 equals V2, which equals VT. It's all the same, because we're going across, the voltage drop across here is the same here and here and across the circuit. So what we can do is say, well, these V's are all the same, and I could just replace this. If I multiplied everything by V, multiplied by V, I'm sorry, so if I multiply by V, and by V, the V's cancel. So we're left with 1 over R total will equal 1 over R1 plus 1 over R2. And if we have more resistors in parallel, it becomes R3, R4, and R5. And so here we have our equation. 1 over R total, or equivalent, will equal all the other resistors. And in series, we just had to add them. But in parallel, we don't. Because one of the things that's interesting is that, let's say we have one resistor going through the circuit. When I bring in another circuit, another resistor I should say, it makes it easier for the electrons to go this way and this way. And so we get more current flowing. And that's different than just adding the resistors. So you saw how we did it algebraically. And it's not too hard. This math works out the same as the kind of math we did when we did the lenses with 1 over F equals 1 over P plus 1 over Q. You have to watch out. So you must take the reciprocal of your answer to obtain the value of the equivalent resistance. So once you get 1 over, you add it all up, you're going to have to take the reciprocal. And the total resistance, which is kind of weird to think, the total resistance of the circuit is less than the resistance of any one of the pieces. Here the total is always bigger than any one of the pieces. On a parallel circuit, it's always less than any one of the pieces. And here on your page 643 is a good summary of the difference between series and parallel and how the math and the equations work out. Now let's take a look at example on page 644 in your book. So we have a bunch of light bulbs again, but this time they're wired in parallel. And you can see how they've drawn the circuit here. And they've drawn the resistances off to the side and the voltage here of the battery. So they want us to find the equivalent resistance, the total resistance of the circuit, and the total current. Total resistance and the total current. So the first goal is to find the total resistance, which 1 over R total or equivalent will equal this. Well, here we go. We've got 1 over each one of these different resistors. Now this is where the math gets a little bit tricky. The textbook likes to take and say, well, 1 divided by 2 is 0.5, and 1 divided by 4 is 0.25, and 1 divided by 5 is 0.2, and 1 divided by 7 is 0.14. Then add up all those numbers, and you get 1.9. Well, the reciprocal of that answer is the final answer, so then you have to take 1 divided by that to get this answer. It is also possible just to add up these fractions and then again do the 1 divided by, and you'll get that answer. So most students don't like doing the math this way. They find it confusing, so you don't have to do it this way. You could just keep it in fraction form, add up your fractions. The other thing is watch out what your calculator is doing. Make sure you know. So once we calculate our equivalent resistance, then we can use that to calculate our total current. So we just take the V equals IR equation, solve for I, and calculate it. Once we know I, we can multiply it times the voltage, and we can calculate the power. All right, so here are the answers for this page, page 645. And then there is page 646. And there are some answers there. All righty. Next section is a little more complex. Hello, physics. Here we are in chapter 18, section 2. And before we dive into it, just want to point out this little article right here. I encourage you to read about semiconductors. And really, it is the transistor that makes things work. And this just scratches the surface of explaining those things. And I encourage you to check it out. You can see here the idea of what they talk about with the transistors. And they get quite complicated. In fact, this circuit here that I've shown you before, you'll see that there's one right there. So our section is on resistors in parallel and in series. Actually, we're going to talk about series first. And all series means is that there's only one way for the electricity to go. So as the electricity leaves the battery or the generator, it goes from one thing to the next thing to the next thing. It's like a trail, and there's only one path, and you either have to climb over the rock or whatever you're climbing through, you have to go all the same direction. There's no other way to go. So an example of that is at the bottom of your text on 637, where battery is hooked up to 2 light bulbs, and one comes right after the other. Notice again that the wires are curved, but in the drawing, they are at right angles. And so the electricity leaves the battery, goes around, and has to go through both resistors before it can make it to the other side. Well, also a reminder that the voltage of the battery, like this is a 9-volt battery, so the potential difference is 9 volts from 9 to 0, and it has to go through these resistors, and the current will, the whole equation that we always use is V equals IR. Since we know the voltage is 9 dropping across here, we would have to figure out both the resistors that it has to go through to get the total resistance. And that's what it's talking about on our other page. So it talks about equivalent resistance. We have to find the total resistance of the circuit because of this V equals IR scenario. And there's a diagram here showing you that as the electricity goes around the circuit, it has to go through both resistors. That means, as from the circuit's perspective, this is a total resistance. So we can mathematically take these two and combine them and call them one resistor. And the math for that is the total resistance or resistance equivalent is equal to all the resistors that are in the circuit in series. So in this case, the total resistance is always bigger than any one of these things because they all get to add together. All right, so when it comes to doing calculations, it's really pretty straightforward. But let's take a look at our example. A 9-volt battery is connected to 4 light bulbs. As shown on the right, the equivalent resistance for the circuit and the current in the circuit. Find the equivalent resistance for the circuit and the current in the circuit. So we're going to try to find R and I. Use the equivalent resistance to determine the total power dissipated in the resistors. So we've got to find the total power. Well, we're given 4 different light bulbs. They are not all equivalent in resistance. They're all different. We know the battery is 9 volts. So we're given 9 resistors, the 4 resistors. So what's the total resistance? Well, that part is easy. We're just going to take and add all the resistors. Now just a note here, looking at the diagram, the electrons have only one path to go, and so this is in series. They could have drawn it lots of different ways, but notice that there's always right angles, even though the actual circuit itself has no right angles in it at all. And the resistors could have been drawn here, drawn up there. The diagram could be drawn this way or whatever. So there's lots of right ways to draw the circuit. But we just simply take all those resistances and we add them up together. So we're going to say this one plus this one all the way across. The total resistance is 18. So now we know the voltage is 9 and the total resistance is 18. Using this equation V equals IR, we algebraically divide by R. So you get I equals V divided by R. And we can figure out how much current is going through this circuit. Now I'm going to flip back and point out that if we know how much current is going through the whole circuit, we also know how much current is going through each individual resistor. Why? Because any electron that goes through here has to also go through here and here and here. Each time, I like to call these, in analogy of water, these are all little waterfalls. So you fall down this waterfall, then that waterfall, then that one, and that one. Finally, you're at the bottom, and you flow into the bottom of the battery. So the current, if we know it in the circuit at all, we know it in all of them because it has to go through them all. So now that we know the current, now we can do the last part where it says find the power. Well, power, as you go back to page 608, you'll see that there are several different equations, and the book chose to use power equals V squared over resistance, which you can do this way. 9 squared over 18 turns out to be 4.5. There's also another equation we could have chosen, power equals I, which we got right here, and we know the voltage is 9. So we could have done this problem without having to find the resistance in this case. Actually, no, we'd have to find the resistance to get the current, but we don't have to use it here. We could use just current and voltage, multiply them together, and we get the same answer, 4.5 watts. All right, so there is the problems. Here are the answers. And just a note here on number 4, it talks about 4 speakers, so you have to remember that the resistance is 4 times that resistance there.